So what I have is my collection of atoms. Let me draw them as points. And you see these atoms are all moving in random directions. And what I do is basically arrange laser beams in every dimension. So let's say this is in one dimension. Imagine I do that in this plane. So I've taken care of the plane. Then I also look at in the direction which is perpendicular to my plane. So I'm representing it like this. So essentially I have six laser beams, all trying to confine these atoms from going away. So every time these atoms make forays towards the laser beam, right, it gets a kick in the opposite direction. These atoms, as they make forays in all kinds of directions, so you see that wherever if they move away, they meet that beam. Whereas I want to arrange situations wherein the is such that it is basically not allowing this collection of atoms to go away from this region where I'm going to cool. Doppler. So where is the Doppler in this business? Okay, so what is Doppler cooling? So the Doppler cooling is basically utilizing the Doppler effect, wherein what happens is depending on your motion. So, for example, you are an atom, and the light is coming towards you, and if you are moving away from the light, you see that the light is actually redshifted, right? Whereas if you are going towards the light, then you see that the light is actually blue shifted, right? Think of it the other way around. Imagine there is a source of light which is moving away from you. In that situation, you will see that the light which is reaching you is redshifted. That's how we know that the universe is expanding, and so forth. So there is a Doppler effect depending on your relative motion between uh, uh, the source of light and you, right? So what one does in Doppler cooling is the following. Remember that if I come in with the atom, okay, which this particular atom is being bombarded. Let's look at one dimension from two sides. Imagine this is laser omega 1 and there is another laser omega 2, which are coming from two counter propagating directions. And you see that if my atom has got a velocity v equal to 0, then of course the interaction between both of these lights is equivalent. On the other hand, what I really want by design is that if my velocity of my atom was in this direction, okay, so this was, so what I really want, if this is my velocity v, and again, I have the same situation. I have omega 1 coming from this direction. I have omega 2 coming from that direction. What I really want is that this atom should interact with this photon on the left more than the photon on the right? Only then you're going to get, due to absorption of this photon, of the left photon, you're going to get a force. So what I want really to happen is that force due to one should be larger than the force due to the second photon. I hope this is clear. So what I want is my force due to one photon number 1, should be larger than the force due to 2, right? So how do I arrange this? I don't want this atom to absorb the omega 2 photon, because in that case I will essentially reinforce this original motion which is to the left. What I want is that this atom should actually absorb the omega 1 photon primarily, so that its motion towards that direction is impeded, right? That's precisely what is the notion. So what one does is selects the photon energy and the atomic energy carefully. So imagine that this is my atomic energy, and what I do is choose my photon energy, that is my omega L is less than omega 1 2. That is the choice I make. So what would happen is that if my atom is moving towards the left, it would see this omega 1 light, which is coming towards it, as blue shifted, right? Because now there is a relative motion between the two. That means this same omega L or omega 1 in our situation is going to appear to be on resonance with the atom when the atom is moving towards it, right? So one is basically utilizing this Doppler shift in the frequency of the incoming photon to actually make that process of absorption happen, so as to get a definite kick in the direction opposite to its motion, right? So the arrangement, so think of it energetically. What you have is, to begin with, you have the atom absorbing a photon omega 1, which is smaller than omega 1 2, and as a following step it would spontaneously emit. Omega 1 2 is going to be given away. Clearly omega 1 2 is larger than omega 1. That would mean what? That this extra energy has to be brought out by the atom in some manner, and what it does is basically it basically uses the external degree of freedom, which is its motional kinetic energy, which is converted, and the photon that goes away, because spontaneous emission carrying away this energy actually carries away this little deficit, which corresponds to the energy gotten from the external degree of freedom, which is the kinetic energy of the atom itself, thereby lowering its kinetic energy. You understand? So you see that even in terms of energetics, this works out very well. And of course, the other way around is not going to work out, because you see that the spontaneous emission photon will always be just omega 1 2, and if the photon carries away some amount of energy and the original energy was larger than that, that is, if omega 1 was larger than omega 1 2, then that remnant extra energy would be converted into the atomic motion itself. So you see, that is not going to work. What is going to work is this red shift, which is associated with the it's a red shift which is associated with the absorption, the process, which is basically what is going to effectively cool down the uh, atom, and give away its extra kinetic energy, is carried away by the photon. Of course, the spontaneous emission itself leads to a random motion, which leads to heating, but then we will get back to that in just a moment. So let me again re-emphasize this just a little bit, that my omega laser 1, okay, appears very clear. So omega L1 appears to be omega L1 plus omega L1 times the shift, Doppler shift, where v is the velocity of the atom towards it. So this obviously is closer to resonance than the original omega L1 which we had chosen. All right. So now so what you have is basically a force that is proportional to velocity. Okay, I can write it in another manner, that this force is actually minus alpha as in some sort of a frictional coefficient, times velocity. So you have seen forces which are dependent on velocity, and they are essentially frictional forces. Now it so happens that my alpha becomes alpha max, right? It takes a maximum value. If I choose my detuning delta, right, it depends on how detuned you are from the excited state. If my detuning is minus, detuning magnitude is basically minus gamma by 2. My alpha is also proportional to the intensity of light, which is the intensity of the laser. This is how you get. And so remember that the mean force that is acting on the atom, is averaged over many absorption and emission cycles. What I have is, I'm plotting force now as a function of velocity of the atom. So you see that because of the laser 1, right? My force is such that it largely peaks when my velocity is finite. By the way, velocity v equal to 0 is here, whereas my the laser 2, the one which is counter propagating in that direction, actually peaks symmetrically at a different point, and such a way that my effective force is essentially somewhat like that, right? And now you ask, what is the width? Where is this width coming from? This width essentially is gamma, right? Because that's my spontaneous emission width, gamma. This width is actually gamma. All right. So you see that and this slope of this curve, right? That's important. And that slope is essentially alpha, right? My frictional slope. So my force is essentially negative of the velocity. Remember that v equal to 0 is this axis. You've got negative velocities where you're moving away from the x-axis in the left direction, where positive velocities you're moving away towards the right, and that's what gives you the force. Now you see there is another competing, right? The other competing issue is that of heating rate. If you look at the heating rate, that essentially it leads to the increase in the distribution of momenta. Okay, so I'm calling that as related to the heating rate is related to the diffusion, because what it does is basically gives a random path to this collection of atoms. So there is a diffusion coefficient one can associate it with that, and this diffusion coefficient itself is proportional to the intensity of light, because more the number of this indeed is true for low light levels. So you see that the diffusion coefficient is also proportional to the intensity of light, so that the overall temperature which I get, you see that you can clearly see that my temperature is proportional to D, because greater is the diffusion, greater is the temperature, greater is the spontaneous emission, that is the diffusion rate, and it is inversely proportional to alpha. Now you can clearly see that my alpha being proportional to intensity and D being proportional to intensity, you see that this quantity, the temperature, becomes independent of the intensity of the laser light. So it's basically what happens is one can get effectively independent of the laser light, one gets a low viscous confinement of these atoms, and the typical temperatures, as I told you, for sodium would be like 240 micro Kelvin one can basically obtain, and similarly one can. So how do you associate this? So remember that, so this the variation in velocities. So you see there is a certain capture velocity within which this will happen, right? And there is a certain variation in the velocity which is given. So you see that this kb times T Doppler, that is temperature associated with Doppler cooling, is essentially governed by this h cross gamma by 2, which is basically governs the width of the width of this forces which confine the atom, and this temperatures is what leads to this 240 microkelvin for sodium, and similarly it leads to for cesium this T Doppler uh, is of the order of 125 micro. So these are the kind of temperatures that one usually gets. If you want to get more details of this, I have been just very brief and uh, only basically presented you the skeleton of this business of cooling. You can actually get to the reviews of modern physics. These are the journal, and you can look at volume 70, where there are back-to-back articles by Cohen Tanoji, Stephen Chu, as well as William D. Phillips. These are people who shared the Nobel Prize for cooling. And this is volume 70. You can look at page number 707, page number 685, as well as page 721. I think these are all back-to-back articles, all in the. These are essentially the Nobel lectures of these three people, and you'll get a lot of references there, which you can follow through and get to much bigger details. All right, thank you very much for your time, and I'll get back to you with the next application in the next lecture. Thank you.